Hello everyone. Let me walk you through this week's highlights on optics. So let's start off here with mirrors. So here we have this blue line that's this mirror, and we have this orange line coming in called the incident ray. This is the light ray that's traveling towards the mirror. And of course, here is the reflected ray. Now, we're always going to draw this normal dotted line here because this is how we're going to measure the angles that's going to be coming in or leaving. So the angle of incidence here, theta I, is the angle from the normal line to the incident ray. Remember, the incident ray is the ray of light that's coming towards the mirror. And the reflected angle, theta r, is the angle from the normal to the reflected ray. Now, for a mirror, the incident angle is always going to be equal to the reflected angle. And this is the law of reflection. Now, there are two categories of reflection. There's diffuse reflection, where the surface is kind of scratched or really bumpy, where the light comes in and it kind of bounces off in all different directions. This is going to give you a fuzzy or even no image at all. The other type of image is a specular reflection. This is going to give you a sharp image, like the image that you see in the mirror in your bathroom. Now, the speed of light in a vacuum is this constant, 3 times 10 to the 8th meters per second. Now, but the speed of light is going to change when it travels in a different material. Think about the wave of water in a lake versus the wave of water in a muddy pond. The speed of the wave is going to be different because the materials are different. And the same thing happens with light. We have an equation to calculate what this velocity is going to be. V equals c over n, where v here is the speed of light in a medium. Now, medium is a fancy physicsy term for material. C, that's the speed of light in a vacuum. That's this number I mentioned earlier. And n is the index of refraction of that medium. Now, this dictates a lot of different properties of a material, and one of them is how fast light travels in that material. Here's a table of different indexes of refraction. So for water, it's 1.33, oil, 1.47, diamond, 2.4. Now for air, I say it's approximately 1 because air is mostly a vacuum. Now, it is slightly larger than 1, but in this class, we're just going to use 1 for the index of refraction of air. All right, so let's calculate the speed of light in water. We can just use our equation, V equals C over N. C is 3 times 10 to the 8th. N for water is 1.33, and we arrive at 2.25 times 10 to the 8th meters per second. Now, light also does something else when it travels from one medium to another. It's going to bend and change direction, which you can see here in these kind of images. This is called refraction. When light bends, it's called refraction. So to help you understand this, I have this analogy here of this lawnmower, and your book does this as well. So this is this push lawnmower. So here's the top-down view of this lawnmower. So as it travels from sidewalk into grass, you can imagine that it's not going to travel as fast in grass because you have to push it through the grass, okay? Much faster in the sidewalk. Now, when this first wheel goes into the grass, it's going to travel a little bit slower than the wheel that's still in the sidewalk. We're just going to angle it slightly more towards the normal line here. So here's another example. Now we're in the pavement going into sand. So from fast into slow, this is our push lawnmower with the two wheels. So when it goes into sand, the right wheel is going to travel a little bit slower, causing the angle to shift closer towards the normal line, refracting this direction. Well, if we go from sand, which is slow, into pavement, which is fast, now this right wheel is traveling faster than the left wheel. It's going to angle it away from the normal, this direction. So depending on whether the light's speeding up or slowing down is going to dictate what direction the angle of the light's going to change, either towards the normal or away from the normal. Now, we can calculate directly what these angles are going to be using Snell's law. So this is medium 1 on the left, and on the right is medium 2. So we have our incident angle of theta 1, and this is index of refraction n1, and our refracted angle theta 2, and index of refraction of material 2, n2. And this is Snell's law here. So n1, index of refraction medium 1, theta 1, that's the angle 1 here, index of refraction medium 2, and angle 2. So n1 sine theta 1 equals n2 sine theta 2. Let's put this into practice. Let's figure out what this refracted angle is going to be when light is traveling from water into oil. So here we have an incident angle of 20 degrees, and I know the index of refraction of water is 1.33, and the index of refraction of oil is 1.47. Well, what's this refracted angle going to be? Well, we can just use Snell's law. n1 sine theta 1 equals n2 sine theta 2. We have everything here except for sine theta 2, so let's just plug those numbers in. And then let's just divide 1.47 to both sides, plug everything into our calculator, and we get the sine of theta 2 equals 0.3094. Now, we want to get what this angle is, so we have to do some math to get rid of this sine function. And to do that, we take the inverse sine of both sides. So that leaves us with theta 2 equals the inverse sine of 0.3094. And when you type that into your calculator, you get 18 degrees. Now, I want you to be very careful here. So be sure that your calculator is in degrees. So there's a mode button here that you can click to change it. You can also test this by plugging in the sine of 90. Be sure that your calculator gives you the answer of 1, and that will double check that you're actually in degrees. Likewise, to do an inverse function, you click second and then the inverse, depending on your calculator. And so test this by doing the inverse sine of 1, and be sure that your calculator outputs 90 as the answer. So please double check this. I would hate for you to do all the physics correct and then just get the wrong answer because your calculator is in radians and not in degrees. Something else strange happens when we go from a slow medium into a fast medium. So here we're going from water into air. So as you can imagine, as I increase my incident angle, my refracted angle is also going to increase. Well, there comes a point where the refracted angle is exactly parallel to the surface. If I increase my incident angle even more, then there's no refracted angle because it's no longer in the air. And when this happens, 100% of the light is going to be reflected. And this is called total internal reflection. You can see this rod of glass here and this laser beam bouncing through this glass in total internal reflection. This is also how optical fibers work. They shine light in at a very specific angle to get it bounced through the optical fibers. So we're keeping nearly all of the light as it passes from one end to the other. So let's load another example here where the answer is going to be total internal reflection. So here we have water going into air, and our incident angle here is 70 degrees, so it's quite large. And I'm asking you, what is the refracted angle? So let's jump to Snell's law. N1 sine theta 1 equals N2 sine theta 2. We have everything here except for theta 2, so just like the previous example. And we're going to plug everything in, and we arrive at sine of theta 2 equals 1.25. Again, to get rid of this sine function, we take the inverse sine of both sides, and we arrive at theta 2 equals the inverse sine of 1.25. Now, if you plug this into your calculator, you're going to get an answer like error domain. And that's because there is no number that will give you the sine of an answer of the sine of an angle equals 1.25. This is impossible. It's not physically possible. What this means is that this is undergoing total internal reflection. So there is no refracted angle because it's all being reflected. So when you get this, don't think that you did something wrong. This just means that the angle is totally reflected. Well, another interesting thing happens is that the index of refraction of light is different for different wavelengths of light. Now, when I say wavelengths of light, I also mean color, because different wavelengths also mean different colors of light. And so when we plug into Snell's law, let's say we have white light, that is all visible colors of light. If the index of refraction is different for red versus blue light, then the angle is going to be different. And so when the light comes in, if the angle is different, then the red light is going to bend at a different angle compared to the blue light. And when this happens, if we shine white light through a prism like this, the light separates out into a rainbow that we're familiar with. Here's the equation slide. The law of reflection, the incident angle equals the reflected angle. Snell's law, as well as the speed of light equation we have here. All right, I hope this helps.